Is anyone will confirm that I'm available or not? Yeah, wonderful. Please do confirm this. Hello, good evening, everyone. Please do confirm once that you can see me, you can hear me, as well as you can see these slides. Hello. So confirm once that you can see me, you can hear me, as well as you can see this presentation. Am I audible? Let's also please do confirm once. I need one or two more confirmations. That you can see me, you can hear me, as well as you can see this presentation. So much. Start. Very good evening, everyone. There is some distortions in the voice. Okay, we try. So now I think it would be more clear. No distortion should have been there. Okay, good. Okay, good. We'll just start. Just 1 second. Okay. So, very good evening, everyone. My name is Ambuj. I am a research scholar at Agriculture and Food Engineering Department, IIT Kharagpur, and I will be taking your live interactive session for the course Data Analytics with Python. This course is taught by Professor A. Ramesh from IIT Roorkee. Okay. And what we'll be doing in this particular session, I'll be solving some of the objective type of questions based on previous week's content in front of you all. Okay. And you shall also try. First you try, then we'll discuss in detail. Okay. And after that, what we'll be doing, I'll be walking you through some Google Colab notebooks, whereby you will get some idea that how the uh, things are implemented practically. Okay, we will go through the coding part as well as other type of different problems as well as different syntaxes, different attributes, different changes which we can just make, and we will try to strengthen our concepts regarding the practical implementation of these concepts. Okay, so this is the agenda. Okay, let us start by the first question. Okay, first question is this one: the model developed from sample data having the form of this particular form y equal to b0 plus b1x, that is known as regression equation, correlation equation, estimated regression equation, or regression model. Okay, please be very thorough with all these regression models. These are the fundamentals of machine learning, and even in deep learning, if you want to switch to these particular domains of AI, you have to be very thorough with the regression modeling. Okay, modeling and in particular regression. Okay, that is very, very important for you all. Okay, to try to provide your opinions. Okay, in the chat box. Regression equation. Okay, good. Okay, okay. Mixed responses A and C. Okay, good. Do try to provide your opinions. Okay. Meanwhile, I'll admit some of your friends. It is my humble request to you all. The session is starting at 6 o'clock. Join it on time for the maximum benefit. Okay. Wait and see. Now you try to see. Question in itself is very fundamental. Okay. Model developed from sample data having the form y equal to b0 plus b1x is known as regression equation, correlation equation, estimated regression equation, or regression model. Okay. And from the responses which you have provided, I can see here it is a mix of A and C. Now we try to see. The correct option would be estimated regression equation only. That would be option number C. It won't be A. Why so? Because given question is in the form of y hat or simple y, and b0 b1 are the estimated coefficients which are obtained from the sample data. Okay, so this in general is the line, same line, y is equal to mx plus c. Okay, so true population regression modeling is this one, b0 plus b1x plus epsilon. Okay, estimated regression equation from the data is y hat equal to b0 plus b1x. Hence the correct option is estimated regression equation. Okay. We'll analyze what is the terminology, why the answer is like that. Okay. We'll just do it. Okay. See, try to see here model and the estimated equation. These are two different things. Okay. In case of your simple linear regression, you have to differentiate between the population regression modeling. Okay. Just 1 second. Yeah. In simple linear regression, you have to clearly differentiate between population regression modeling. Okay. That will be your nothing but y equal to b0 plus b1x plus epsilon, where y is the actual dependent variable. B0, B1 are the population parameter or your unknown constants, or epsilon is in general your random error term. Okay. See, this equation will try to describe the true underlying relationship in the population. It is including a particular stochastic term, which is epsilon, or also known as the regression modeling error. Okay. But your estimated regression equation, which is obtained from your sample data, would be y hat equal to b0 plus b1x. Okay, where b0, b1 are the sample estimates of b0, beta 0 and beta 1. Okay, obtained from here. Beta 0, beta 1. Okay, no error term here is expressed. Okay, here there is no terminology like plus epsilon minus epsilon type of bit. Okay, this equation is obtained after applying the least squares to the sample data, because it will use the sample statistics b0 b1. It predicts y hat, that are the fitted values, and it contains no error term. Okay, so it is also known as your estimated regression equation. Okay, the regression equation is this one. Okay, in general, it is too general. It could refer to population equation, sample equation, and definitely that is not the case. Okay. Uh, when it was your correlation equation, it is also incorrect. Correlation is equation is often expressed with R. Okay, that is your coefficient of determination. Okay, so that won't be here. Regression modeling, regression model, I have told you it contains your particular term, which is your epsilon. Okay, it contains your stochastic error term, which is epsilon. Okay, so a regression equation is a two general term that is directly obtained. Just 1 second. No. Regression equation in general is a two direct term. Okay, that is obtained from your data points. Okay, population equation or your sample equation. Okay, it will specifically state the developed from sample data. It must be of estimated form. Okay, and your correlation equation, it is definitely incorrect. Okay, correlation will measure the strength of the linear association. It does not provide an equation for prediction. Okay, and regression model will always include your stochastic error term, that is your epsilon. So estimated regression equation, that is the option B, would be correct. Okay, that equation is y hat equal to b0 plus b1x, where b0 and b1 are the sample estimates of beta 0 and beta 1, which is the population regression modeling equation. And it also contains an error term or the stochastic term, which is also known as epsilon. Okay, so try to keep in your mind. Okay, now you try to see, this one is the conceptual summary. Okay, regression modeling, what is the equation, whether it comes in with an error term, yes, whether it is based on sample population, yes. Okay, estimated regression equation is this one. Okay, it contains error term, no. Based on sample, yes. Final answer is your estimated regression equation. Okay, that is the thing. Yeah. Okay, now you try to see the next question. Okay. Yeah, the model developed from sample data in the form of y hat equal to b0 plus b1x is known as yes. This is because b0, b1 are calculated using a sample data from the entire population. Yes, the question is used to predict the value of the dependent variable y hat based on the dependent value of the independent variable x. So the correct answer is C, estimated regression equation. Definitely you are correct. Okay. Let us move to the next question. In the regression analysis, which of the following is not a required assumption about the term epsilon? The expected value of error term is 1. The variance of error term is the same for all values of x. The values of the error term are independent or the error term is normally distributed. This you try to solve. दादा थोड़ा एसी चला दीजिए गर्मी लग रही है थैंक यू यस Yes, some noise is coming, background noise is coming or not? It shouldn't come. I don't think so. If it came in between, I'm not sure about it. It should not come now. If it is coming for others, for all, then please tell me. I'll try to look forward for the solution. I'm assuming then it is fine. Everything is fine. Since I don't see any noise in the feed, I can see the video clearly also. So I'm assuming everything is fine. Yeah. Regarding this particular question, in regression analysis, which of the following is not a required assumption about the error term, which is the epsilon? Okay, just 1 second. Yeah. Which is not the required assumption about the error term epsilon. Okay. So correct option would be option A only. Okay. So try to see the expected value of the error term is 1. No, you cannot say like this. Okay. See, in your classical linear regression modeling, assumptions about the error term epsilon are very, very specific. Okay. For the model, you have the equation y equal to b naught plus b1 beta 0 plus beta 1x plus epsilon. Okay. Classical assumptions are zero mean. First of all, you have to understand it would be a zero mean. Zero mean is the very first assumption which we are trying to make. Okay. Yes. Zero mean is the very first assumption which we are trying to make. It means that the expected value of the error term has to be 0. Okay. Not equal to 1. Okay. So it will try to ensure that the regression line is correctly centered and the estimators are unbiased. Okay. Another thing is homoscedasticity, which means constant variance. It will try to assume that variance of the error term is standard uh, is sigma squared. Okay. Variance of the error term should be equal to standard deviation whole square or sigma square. So the variance of the error term must be constant for all the values of x. This is also known as homoscedasticity. Okay, homoscedasticity. Okay, it will try to, if your variance changes with respect to your x. Okay, this particular term, if we are having we are having heteroscedasticity, which will violate your assumptions. Okay. So option B is indeed a required assumption. Okay, what were the options? First one was expected value of the error term is 1. No. Okay. It's not 1, it's 0. Okay. Then your second assumption was homoscedasticity. The variance of the error term is same for all the values of x. No. It has to be always there. The question is asking, not a required assumption. The preliminary condition for homoscedasticity is this particular one. Variance of the error term is same for all the values of x. Okay. Variance would be definitely sigma square. It will not change with respect to x. Then your third term. Okay. Third term was your independence. Okay. Covariance of the error terms. Okay. Epsilon I, epsilon j is equal to 0. Errors must be independent across the observations. They necessarily should be independent across the observations. This will also prevent autocorrelation. Autocorrelation means the errors are correlated with each other. Okay, so it should not be there. Okay. So it is written the value of error term are independent. Yes, it has to be a preliminary condition. Okay. The normality, the error term is normally distributed. Yes, normality has to be there for the error term. Normality is not required for estimating coefficients of ordinary least square regression, but it is required for exact hypothesis testing, which are t-test, f-test in your small samples. In your case of your standard regression, standard textbook regression assumptions, normality is usually included. Okay. So evaluating each option, option A has to be incorrect. All the rest options have to be a definite assumption. Okay. So final answer is A. The expected value of error term is 1. It should not be 1. It should be 0. Okay. That is that. Yes. The expected value of the error term is 1. No, it is not 1. It is 0. In regression analysis, the expected value of the error term should be 0, not 1. Yes. Definitely, your explanation is correct. And yeah, this explanation is also correct. So you all are correct. Noise issue, if it is there, please point it out once again. Rest, I think everything is fine. Okay. Let us move forward. Try to solve this particular question. A regression analysis between the sales. Sales means Y in your dollars. Okay. Y in $1,000 and advertising, that is X is in dollars, resulted in the following equation, which is y hat equal to 30,000 plus 5x. Above equation implies that an increase of $5 in advertising is associated with an increase of 5,000 in sale. Increase in of $1 is in advertising is associated with an increase of $5 in sale, or increase of $1 in advertising is associated with an increase of $35,000 in sale, or increase of $1 is advertising is associated with an increase of 5,000 in sales. So do try to solve this particular question. Yes. D, okay, D is your call. Good. Rest of the students should also try to answer. Okay. The rest of the students should also try to answer. Very simple question is there. To try to see the things. Put $1 value. Okay. In case of your advertising, that is your X. Try to see what is the change in Y. Okay. Okay. Others also, please try to be more interactive. Give your opinions. Not necessarily at the very first attempt it should be correct. Okay. B. Okay, good. So the correct option would be D. Okay, it won't be B, it would be D. Okay, it would be D only. Okay. Now try to see. You have been given a regression equation y height equal to 30,000 plus 5x. Okay. First of all, you have to understand the units y is sales in terms of $1,000. X is your advertising, that is also in dollars. Okay. This particular information is very, very important. Now interpret the slope. Slope is 5. Okay. Means for one increase unit of X. Okay. Y will be increasing by 5 units because slope is 5. Okay. But you have to remember that it is in $1,000. So now you try to see their increase would be in 5 times of $1 increase, that is 5 times of $1,000 increase, that is $5,000. Okay. So final interpretation is this, that $1 increasing in advertising is associated with 5,000 increase in sales. Okay. So correct option would be your D. If it feels difficult for you, then there is no issue. I will try to demonstrate you one another thing. You were asked that X is in dollars. Okay. Y is sales in 1,000. So let us say Y1 is your 30,000 plus 5x1. Now your Y2, it is what is trying to say. What the equation is trying to say is that $1 should be increased. Okay. $1 should be increased in your advertising. Okay. $1 should be increased in advertising. Okay. From these two equations, if you try to calculate y2 minus y1, what you will get? You will get 5 only. Okay. If you try to subtract y2 minus y1, you get 5 only. But what is the unit of y? It is in $1,000. So it will ultimately mean $5,000 because y is sales in $1,000. This also very easily you can see here. Rest any another method like plotting graph is also an excellent method. Okay, so you can try with that also. Okay, let's move forward. In case of your regression and correlation analysis, if R square is 1, then SSE is SST Both are equal. SSC is 1, SSR is SSC, or SSR is equal to SST. Okay. Do try to give your opinions. Okay. In a regression and correlation analysis, if R square is equal to 1, then one person is saying option B would be correct. Okay, let us see what would be correct. We'll just see. Rest others, please try to give your opinions. If University is giving good explanations. Friend Tanu, why are you giving your crying emoji? Something, any issue is there, please try to express it, not through emojis, but you can just write it down. Related to studies only, academic issues only. Okay. D, okay, D, good. Yes, if R square means equal to 1, it means the regression model is explode 100% of the total variation in the dependent variable. Since R square is SSR over SST equal to 1, implies SSR is existing. Okay, SSC is equal to 0, though no error is there. Data points lie perfectly on the regression line. Section D. Okay, very good. Nice explanation. Okay. Option number D. Good. Yes, indeed. Option D would be correct. Okay. If you try to fundamentally decompose the variability in the regression, okay, SST is SSR plus SSE. Okay, that is correct. SST is total sum of squares or the total variation in Y. SSR is regression sum of squares. SSE is error sum of squares. R square is 1 means R square is SSR over SST. R square is 1 means SSR over SST is 1 means SSR is equal to SST. What does this mean? It means all variation is explained by the regression line. There is perfect linear relationship. All points lie exactly on the regression line. No residual will exist. SSE is 0. Since SST is SSR plus SSE, SSE is 0, SST is SSR, SSR is SST. So option D will be correct. Rest all of the options will be incorrect. Moving forward, SSE. Okay, SSE is same, this one only. Error sum of squares. SST is total sum of squares. SSR is regression sum of squares. Okay. SSE. Okay. Sum of square errors is larger than SST. It can never be larger than SST, smaller than SST, equal to 1 or equal to 0. This you try to explain. A, and A. Okay. A. Okay, total sum of squares, total sum of squares, SST, relation sum of squares, the sum of the squared errors, SSC is part of SST, equal to SST smaller than SST, it can be zero, but SSC can never be larger. This still has conclusions is library. Yes, still whatever. This is also that. This is version. Thank you very much. Yes, indeed. It, the correct option would be larger than SST. Okay. SST is SSR plus SSC. Okay. SSR can be greater than equal to 0. SSC can be greater than equal to. If you try to compare SSC and SST, SST is SSR plus SSE. When you try to rearrange, SSE is equal to SST minus SSR. So your SSR is greater than equal to 0. Hence, SSE has to be less than SST. Okay. So that is the thing. SSE can be equal to SST. Okay. When SSR is equal to 0, that is there is no explanatory power. SSC can be equal to 0, but it can SSC can be any non-negative number, but SSC cannot exceed SST. That is the thing. Okay. Evaluating options impossible. First of all, it cannot be larger than SST. It can be equal. It has to be non-negative number. It can be equal to 0, but never larger than SST. Rest all the possible cases are true. Hence, the correct option would be larger than SST. Okay. Now we'll try to solve this particular question. For the given data, determine the R squared value. Okay. R squared value we have to determine. Data is miles travel, which is 20, 20, 45, 56, 34, 28, 49, and petrol consumption in liter, that is 1352, 1.6, 3.7. Okay. Miles traveled and petrol consumption in liter has been given to you, and you have been asked to calculate the value of R squared. Do try to calculate it. Okay. And if any one is successful, then please tell me what option you are getting. Okay, 0.956 of the value. Okay, you are getting option B. Good. Rest all the students to try to solve. Good, good, good. D and C also 0.945. Okay. Good. Yes, now we'll try to see. It would be B only 0.956. One person is saying point C. Okay. C won't be correct. 0.945 won't be correct. 0.956 would be correct. Okay. You have got this pair data 21, 45, 3, 56, 5. Okay. Then 34, 2. Then 28, 1.6, 49, 3.7. Now you have to compute R square. Okay. R square value. R square value will be equal to this particular thing. Okay, n summation xy minus summation x summation y. Okay, divided by n summation x square minus n minus summation x whole square. So in first bracket, in second bracket, n summation y square minus summation y whole square and the whole. Okay, nobody wants to join? No. Okay, yes. Where R is the Pearson correlation coefficient. Okay. So in case of a simple linear regression, you just have to remember the formula and then apply. Okay. Calculate the Pearson correlation coefficient squared of that particular value, you will get R square. Okay. Now try to see. N is 6. Number of observations is 1, 2, 3, 4, 5, 6. 6 number of nodes are there. Okay. N is 6. Now you try to compute the individual terms, which is summation x, summation y. Summation x means miles, all you have to sum. Okay. For x, I have taken a data variable as miles. Okay. And y, data variable is petrol, that is column number 2. And miles are your column number 1. Okay. Now you try to see summation x will be equal to 20, 20, 45, 56, 34, 28, and 49. Okay. 20, 30, 45, 56, 34, 28, 49. Okay. 20, 45, 56, 34, 28, 49. That is 232. Summation y is 13, 1352, 1.6, 3.7. Okay. 1352, 1.6, 3.7. That is 16.3. Then summation x square. Okay. Squared all the values and then add. Simple thing is there. Means 20 square, then 45 square, then similarly 56 square plus and so on up to 612. That is coming 9902. Summation y square, you try to calculate 1 square plus 3 square plus y 5 square plus 2 square. Okay, that is 55.25. Now summation xy, okay, x into y and sum of that. Okay, is 20 into 1 plus 45 into 3 plus 56 into 5 plus 34 into 2 and 28 into 1.6. Okay, yeah, that is summation xy. Okay, so summation xy, I have computed the value as 729.1. Okay, so R value, if you try to compute, numerator is n summation xy minus summation x summation y. Okay, so that is 6 into 729.1 minus 232. Okay, multiplied by 16.3. Directly values I have copied from above. Okay, that is 593. Then denominator term is much complicated. N summation x square minus summation x whole square. Okay, so n summation uh, x square minus summation x whole square. Okay, summation x square value I have calculated 9902. That is multiplied by 6 minus 232 whole square. Okay, so that term I have calculated as 5588. Okay, then second term I have tried to calculate 6 multiplied by 55.25 minus 16.3 whole square. Okay. Second term is this one, n summation y square minus summation y whole square. When denominator would be the product of these two values. Okay. That is coming 5588 multiplied by 65.81. That is multiplied and taken under root. That is coming 606.43. Now we try to compute the value of r. That is 593 divided by 606.43. That is 0.978. Okay. But this is R, you have to compute R square because capital R square coefficient of determination is Pearson correlation coefficient whole square. So 0.978 whole square is 0.956 and 0.956 is option number B. Okay. Point I think 978 should also have been an option. No, it is not there. But in competitive examination, options are too confusing because the value which you will get just before the final step, that would also be an option so that you can mark it and it would be wrong. Okay, so it's a kind of trap in competitive examinations. Okay, that is the thing. Okay, If any doubt is there, feel free to ask. The rest we can move to the next question. Anshika, if it is clear to you, then please say. Otherwise, please ask the doubt. And rest all students, if any doubt is there, please feel free to ask me. The rest we can move forward. Okay, it is clear. Fine. Let's move forward to the next question. Okay. In question number 6, we will accept the null hypothesis, reject the null hypothesis, can't state any conclusion, or none of them. Okay. Do try to solve it. Okay. We reject the null hypothesis. Okay, reject the null hypothesis. Yes, indeed, if you try to see, it would be reject the null hypothesis only. Okay, why? So, in case of 6, in case of question number 6, you have obtained R square is 0.956. Okay, and R is your 0.978. Okay. In, first of all, you have to state the hypothesis or you have to perform the correlation test. Then only you will be in a position to say whether you are rejecting the null hypothesis or accepting the null hypothesis. Null hypothesis formulation we have carried out in the case of your regression or correlation testing. H0 is rho is equal to 0 and H1 is rho not equal to 0. No linear relationship or there is linear relationship. Then you carry out the test statistic for correlation, which is nothing but for testing significance of R, T is R under root n minus 2 over under root 1 minus R square. You compute the value of T. Okay. T is coming out as 9.31. Okay. R is your calculated 0.978, N is 6. Okay. Then degrees of freedom is 4. And at 5%, okay, level of significance, your critical value of T is 2.776. Since T calculated is greater than T critical, you reject the null hypothesis. Okay. So what we'll try to say, there exists statistically significant linear relationship between miles traveled and petrol consumption. That is your conclusion. You are rejecting the or you are accepting the alternate hypothesis. That will be fair. Next question. All the questions which will follow are connected to question number 7 previously. Question number 6 previously. In question number 6, determine a 95% confidence interval for B1 to test the hypothesis. Okay. If you are not aware about question number 6, I'll just give a screenshot here. Question 7, I think we have solved. Okay. Question number 8 is this one. I will just give this screenshot here. This is your question number 8. Okay. I'm just sharing question number 6 also. The question is in question number 6, determine a 95% confidence interval for B1 to test the hypothesis. Okay, that is the question. This B1 is a small B1. If you are getting confused, I will just mention it here. It is a small B1. This B1 I am talking about, not any other B1. I'm talking about this particular B1. Okay, given 595%, okay, 0.055 is the rate of entry, but just all the students do try to calculate. We one, okay, the one is 0.1061, so that was 0, and then 4, 2, this r square is 0.6. Then we were asking about this question, previous question, I don't know. Everything is correct, but it is regarding which question. I fairly not confident about it with what you try to convey. If it is about this particular question, then the explanation is something else. If it is was about previous question, yes, you are correct. Yes, everything is correct, but it is not in regard to this particular question. Okay. Yeah, this is. We'll see. Okay. Yes, you are getting 0.065, 0.15. Yeah. But you are getting option in this C. C, then C, and Anshita has not written which is the correct option for this particular question. I'm fairly not confident about what she has written. Then B. It's regarding, I think, previous questions. Yeah, B and B. Okay, two B's are there. Okay, take some more time. Try to give a proper explanation. Yeah. You try to see. It would be D. It won't be C. It won't be even B. It would be C. Okay, let me thoroughly solve it. From question number 7, X we have considered miles traveled, Y we have considered petrol consumption, small n is 6. If you try to compute 95% confidence interval for the slope B1, okay, you have to compute this particular B1 using this particular formula, that is n summation xy minus summation x summation y over n summation x square minus summation x whole square. Okay. N is 6 and we have computed it earlier. Okay, summation x we have computed, summation y, summation xy, summation x square. Directly, if I will put the values, then numerator value I can get as n summation xy minus summation x into summation y. That I am getting is 593. Then denominator value is n summation x square minus summation x whole square. Okay. That is 6 times 9902 minus 232 whole square. That is 5588. So B1 value directly I am computing as 593 divided by 5588. Okay. So B1 is coming as 0.106. Okay. Now we have to compute the standard error of B1. Why? Because we have to give a range. Confidence interval for B1 to test the hypothesis. That is what being asked in the question. Okay. So that is why we are going for calculating the standard error. That is SSE over n minus 2 summation x minus x hat square. Summation x minus x hat whole square that we have tried to compute here. Okay, that is nothing. Already we have computed 5588 divided by 6, that is 931.33. Okay. So SSX we will try to compute, that is coming as 931.33. R square is 0.956, SST is 10.968, SSE is 1 minus R square into SST, 1 minus R square into SST value I have computed, and I am getting value SSE is 0.483. Standard error for B1 I am getting as 0.483 divided by 6 minus 2 multiplied by this particular value, that is 0.011. Okay, that value we have computed. Now, critical value for t we will try to compute. Degree of freedom is n minus 2, that is 4. 6 minus 2 is 4. When for 95% confidence interval, t critical value from the table is 2.776. Confidence interval is B1 plus t into standard error of B1. So 0.106 plus or minus 2.776 multiplied by 0.0114. Okay. So that value for lower limit I have computed as 0.074, and upper limit by adding the values 0.106 plus 0.0316, that is 0.138. Okay. So 0.075 or 0.074, that value I am getting in 0.138. Okay. So near about it is coming in option number D. So D will be correct. Okay. So that is the thing. After the class is over, my sincere advice to you is I'll upload the PDF, go through it, do the calculations yourself once again. You are stuck anywhere, feel free to ask in the next session. Okay. That is the sincere advice. Okay. Which you can take from me. Okay. And if here any doubt is there, feel free to ask. Rest we can move forward to the next question, which is very simple. Okay, state true or false statement. The variance of error is same for all the variables of the independent variable. Okay, this is the question. The variance of error is same for all values of the independent variable. This is the question. Okay. Yes, true. Okay. And in the previous question, you will get clarity only if you will revise. Okay. That is the point. Statement is saying variance of error is same for all the values of the independent variable. This is one basic assumption of regression, which is homoscedasticity. So the statement is true. Correct option is A. Okay, good. The rest, all the students who try to answer. Yes, now try to see this statement is 100% true. Statement is the variance of error is same for all the independent variable. Okay. In case of a classical linear regression, one key assumption is homoscedasticity. Variance of epsilon I is summation is sigma square for all I. Means the variance value of errors is equal to sigma square. Standard deviation whole square means variance of the error term is constant. It will not dependent on the value of x. Okay, so if the variance changes with respect to x, the condition is known as homoscedasticity. It will violate the classical assumption. Therefore, the statement which is correctly describing the required regression assumption, okay, it is true. Okay, the variance of error is same for all the values of independent variable. Yes, variance of error has to be same. Okay, that is the primary condition for homoscedasticity that I have already talked about in question number 2. Okay. Next question, which of the following is possible for the coefficient of determination? It can be larger than 1, is less than 1, it can be less than minus 1, or none of the alternatives is correct. You try to solve it. Her square value ranges from 0 to 1, therefore it cannot exceed 1 or be negative since as the correct option is B, it is less than 1. Okay, good. B, A, then B, then B, then B. Okay, the rest all give it a try. B. Okay, good. B. Good. Yes, R square is coefficient of determination, which is SSR over SST. It will try to measure the proportion of total variation in the dependent variable explained by the regression model. It ranges between 0 to 1. SST is total sum of squares. Okay, SST, total sum of squares, that is yi minus y hat whole square. Okay, means it measures the total variation of the dependent variable y. It represents how much observed values will deviate from their mean. Okay, SSR will be your regression sum of squares, which is expanded form SSR equal to y hat minus y bar whole square. Okay, it means it will try to measure the explained variation. It is variation explained by the regression line. Okay. SSE is error sum of squares. Okay, it will try to measure the unexplained variation. Okay, it will represent residual error, that is the distance between actual and predicted values. Okay, yi minus y hat whole square, and the fundamental relationship which holds is SST is SSR plus SSE. Okay, SST is SSR plus SSE. This is known as ANOVA decomposition of the total variation. Okay, SST is total sum of squares, SSR is regression sum of squares, SSE is error sum of squares, R square is coefficient of determination. Now R square is SSR over SST. SSR is greater than equal to 0. SST is greater than equal to 0. SSR is less than equal to SST. And SST is SSR plus SSE. And SSE is greater than equal to 0. Hence R square is 0. Ranges between 0 to 1 only. Okay. It can be larger than 1. No, it is impossible. It has to be less than 1. It can be less than minus 1. No, it cannot be negative. Okay, because R square is never negative with standard deviation with respect to their intercept. None of alternatives is correct. That is also incorrect. Hence, the correct option is always less than 1. Okay, I will try to remember. Okay, and if any problem is there, doubt is there, feel free to ask. Okay. Rest, we'll move to this particular collab notebook which I have prepared. Okay. What you have to do, I will give you the IPYNB file of this particular notebook. What you have to do, you have to search in Google Colab. Okay. Then you have to go here, Google Colab, then go here, upload and browse the location of the file where you have downloaded that particular file which I have shared with you. Okay. So then you try to play with different types of options and what are the facilities which are there in this particular notebook. Try to play with the options with the parameters, whereby you will realize how things are working. Okay. Now, first of all, we have to import all the requisite libraries. Here we are importing pandas, numpy, matplotlib, seaborn. Okay. We are also importing sklearn. Okay. And here in sklearn only there is California housing dataset. Okay. Housing equal to fetch California housing, and x and y is your data as well as the target, and try to print the shape of x and y. Okay. Then from sklearn.datasets import fetch California housing. Then same line is here. The same line is repeated twice and delete this particular line. Okay. How I can do so? Yeah, and delete. Okay. Then also run all, and I think all the cells are producing results. No error is there. Let me check once. Then I'll explain. Okay. Any error is there, first I will resolve that. Then I will move forward. Okay. So we are printing the shape of x and y. Okay. Shape means what are the number of rows, what are the number of columns. Okay. Then we are importing OpenML. Okay. Then fetching the entire dataset from OpenML Boston housing dataset. Okay. So it is having various rows, various columns, and we are just printing the first 5 rows with the, how we are doing it through dot head. Okay. So x dot head and y dot head I have directly printed. It is giving me the first 5 rows. Okay. Of my Boston housing dataset. Okay. Then feature names I have printed. Okay. Means feature names means the column names. Okay. Then Boston dot target. Okay. What are the target values? Okay. What is length? What is data type that we have printed? Then shape I have tried to print. Okay. What is the number of rows? What is the number of columns that I have tried to print? Okay. Then description I have tried to print. Okay. Shape we have printed. Then using the head we have printed. Then here also we are using the shape. Okay. And within one data set, we are trying to uh, create a sub data set, and then we are trying to perform some of the analysis. Okay. Then description using DESCR, we are trying to print what is the description of the entire data set. Okay. Description it has created. Okay. Uh, and then it has provided what is the descriptive idea where from it is downloaded. Okay. Which are the rows, which are the columns, what signifies what particular row signifies what particular value. Okay. Then you are creating a data frame from this particular Boston data set. Okay. Then you are printing the head means the first 5 rows of the entire data set after creating the data frame from the data set, which we have downloaded from OpenML. Okay. Then I am targeting this particular variable. This is my target variable for my UI only. Now target variable, you try to remember it is price. And now I'll try to formulate the correlation of this particular target variable with respect to the all variables. Okay. So extracting the features and the target variable. Okay. First of all, I have created y value variable and the x variable. Okay. Then from sklearn.model selection, I am importing test train split, importing linear regression, mean square, R2 underscore. Okay. And then score. This R square value directly I am importing from sklearn.model selection. I am importing train test split from sklearn.linear model. I am importing linear regression from sklearn.matrix. I am importing mean squared error or R2 score or R square. Okay. So X train, X test, Y train, Y test is test train split. And then directly I have created the random state and test size as 0.2. So X underscore train dot shape, X underscore test dot shape, Y underscore train dot shape, Y underscore test dot shape directly I have printed. Okay. Then linear regression model I have used. Okay, lm equal to linear regression. Okay, and directly I have fitted the linear regression with extreme and y term. Okay, then y predictor. What is the predictor? Which is x test. Using x test, I am predicting the y predictor value using the model which I have fitted with the extreme and y term. Then I am comparing the actual prices versus the predicted prices. Means using the linear regression model. First of all, I have created the linear regression model. Now I am printing the, I am formulating a graph of the actual versus the predicted prices from the linear regression model. Okay. This one is the graph. This one is your 45-degree line which will pass through the origin. This one will be your 45-degree line. Okay. Like this, where I am pointing my cursor, and all the variables, all the values of actual and predicted, if they are lying close to your 45-degree line, that model will be the most accurate. Okay, so that you have to just check. Okay, then delta y is y test minus y pred. Okay, this delta y is nothing but the error from your tested value and your predicted value. Okay, then you are trying to plot the density function. Okay, with the median value that we plotted. Okay, then calculating the MSE, which is the mean squared error, R square. Okay, you will just try to calculate with y test and y predictive values. Okay, so MSE is coming 24.29, R square is coming 0.67. Okay. Then ridge regression. Okay, this is regarding your simple linear regression. Another model I try to plot, that is your ridge regression model. Okay. So in ridge regression modeling, you are importing all the libraries, requisite libraries, likewise only we have imported. Okay. Then that particular data set only I have just tried to use. Okay. Then train test splitting in 80 and 20%. Okay. Then training the linear regression without L1 or L2 regularization. Okay. Then training the ridge regression with L2 regularization. Okay. So ridge model I have fitted. Okay. And I have used ridge with a value alpha, which is the regularization stone. I have used it as 1. Okay. So fitting the model similarly to the previous cell in which I have demonstrated how linear regression modeling is fitted. So similar to that, I have fitted the ridge regression modeling. Then in evaluating both the models means calculating the mean squared error as well as the R square. Okay. So ridge value, okay, and R square value we have calculated. Okay. MSC and R square value we have calculated. Okay. Then what is the scatter plot? Okay, actual versus predicted scatter plot we have formulated. So linear regression MSC is 24.29, R square is 0.67, ridge regression MSC is 24.48, R square is 0.67. Okay. Then import your median mode. Okay, then is man means not a number. Filter wise you try to import. Okay, then you go for median of this particular data. Okay, which we have given median of this particular data. Okay, then sort the data. Okay, then clean the data, then give your sorted data, try to print it, calculate the median value, mean value. Likewise, for different fractions and data variables, if they are provided, you can calculate. Okay. Then you can calculate the standard deviation also. Okay, as well as different other parameters are there. Grades, weights, then weighted mean you can calculate likewise using this particular formula. Okay. These are the different some of the points which I have kept, okay, for demonstrating you that how particular statistical parameters you can calculate. The calculation which you are doing manually from your hands, okay, or you are using your calculator, you can do it with Python also. This is last part is regarding that only. How can you do mean, mode, median, then your geometric mean as well as your standard deviation. This particular demonstration is regarding that. Okay. So I hope everything is clear to you. Okay. If any doubt is there, feel free to ask. Okay, the session is over from my side. Okay, why delta? What is delta and why is it used? Uh, Thank you all for joining the session. If any doubt is there, feel free to ask me. Okay, rest you can kindly leave. Okay, you can join the session next week, sometime same. Okay, now I will hand over to you. Ask as many doubts as possible, and I will try to answer. Yeah. What is delta and why we use it? Okay, just 1 second. You are asking here delta or which type of delta you are asking? Delta in general is error, small del. There is a difference between small del and delta. Delta is in general error. Okay. So where it is written, you just try to tell me. Thereby I will explain there itself. Okay. Which type of delta and which type of use you want to ask me, you just clarify. I don't see any delta neither in the PDF which I have shared now in this particular notebook. Okay. Please point out to the delta, then I'll be in a better position to tell you that how and where it is used. Delta in general is error only. Okay. There is a difference between delta and del. Del is partial derivative. Delta is full derivative or error. Both are used. Okay. So the denomination of delta. Delta keyword which is there in your code above. Okay. But let me find out this delta. Okay. This delta y, this delta y, this delta y, this delta y. Okay. This delta y. You should have said, you should have asked delta y. There is a difference between delta and delta y. Delta y is nothing but the error in y. Okay. Delta y. Delta in general means error only. Okay. And delta y means error in y. It is the difference in the values of test value and the predicted value. Okay. So predicted value, how you are getting, see, try to see the code. Okay. Predicted value you are getting from the model. Okay. And there is a test value. What is the test value? That already you have splitted from the data set. That train test split means the values in 80-20 formulation you have designated. Just give me a minute. हाँ अभी मैं क्लास में हूँ मैं तुम्हें अभी कॉल करता हूँ ओके हाँ मैं क्लास में हूँ मैं तुमको कॉल करता हूँ बाद में ओके हाँ मैं क्लास में हूँ मैं कॉल ओके yes. So delta y, okay, that delta y you are getting as difference of test y test and y predicted value. And then predicted value, y predicted value, how you have given y pre that predicted value you are getting from here. Okay, that test value, y test, okay, that you are already doing this train test split means you are splitting the entire data set in 80% and 20%. 20% data will be separated randomly from the entire data set and that will not be shown to the model. That is the thing here. Okay. Oh, sorry. I spoke so much, but my microphone was turned off. Okay, sorry. I'll repeat. So I was talking about your 80% and 20% test train split. Okay. So here there is now voice must be coming, I think. I have unmuted here. I think voice is coming, right? Audible? Okay, good. Sorry, in between there was a urgent call, that is why I muted. Then I forgot to mute. I am really sorry. I forgot to unmute. I am really sorry. I am repeating my words, no problem. Okay. So here the thing is delta y, y pred. Okay. Where it gone? It is one delta. Go to the delta. Delta. Yeah, this is delta y. Delta y is y test minus y predicted value. Okay. How you are getting the y test? You are getting the y test from your train test split. And this train test split is the particular function which is used to separate the entire data set in 80% and 20% fractions. 80% fraction is used for training the entire data set and 20% is kept aside, okay, for testing. For testing, okay, that is the 20% split, okay. So that 20% data set we have kept aside, we have not shown it to the model. So we will test our model from that 20% values only, okay. That is the thing. So our function, it will use 80% data for training, 20% data is kept aside for testing. So from that, Y test has been created. X train X test, Y train Y test. Okay. And then Y pred, that is Y underscore pred, that value you are getting from the after fitting the model. Okay. In this particular case, you are fitting a linear regression model. That is why it is giving you Y pred value, means predicted value from linear regression model when X test value is provided. Okay, and the difference of these two particular values will be giving you the error in Y. What is the actual error of the model for all the values? From that particular delta Y, you are able to classify the error. Okay. Here it is written MSC dot colon 2F. It only means, okay, that you are directly using the function, okay, to calculate the mean square error, okay, that is pre-built in the model. That is why I have used MSC R2, okay. Otherwise I have to calculate manually. Okay. What is LM? LM is nothing but I have written linear regression model. I have called the linear regression function, and function by value call I have created to the variable name LM. Okay. Here in place of LM, it's just a variable. You can write your names. Okay. Then here also you have to write your name LM dot fit. Then your name dot fit. It's 10 by 2. It's just a variable used for calling the function in Python. Okay. Yes, thank you everyone for joining the session. Okay. Yes. Any more doubts? Feel free to ask. Okay. There is no issue. As many as doubts you are having, feel free to ask. Okay. But clarify your doubts. Okay. At the end of the day, everything should be clear to you. That is my only priority. Okay. This was regarding question number 6. Yes. Yes. Can you tell why we use scatter? Okay. The scatter plot I have created here. Okay. Likewise, why we are using it. See, scatter plot is generally used to compare the values between your actual values and the predicted values of the model. So scatter plot will only give you the idea that how your values or the values are scattered over the entire region. How you have predicted or any particular predicted and actual value comparison, if you want to make, then you can create plot like this. Otherwise, this basic idea of scatter plot is just to give the idea that what is the exact sparse variability in the entire data set that we want to check and we want to measure. Okay, and we want to get a pictorial idea of how the values are sparsely distributed across the entire data set. That is the principal function of the scatter as well as the scatter plots. That is the thing. How do we decide the optimal value of lambda in ridge regression, and what happens if we choose it incorrectly? Okay, very good. Practicing this in Google Colab is enough. Yeah, yeah. This such as PDF along with the codes which I have shared with you, and along with the video lectures which we are just sharing with you all, they will just suffice. Okay, they will suffice for the examination. Okay, no, not anything is uh, outside of this is required. Okay. Just I will create an example and I will try to explain this particular problem. How do we decide the optimal value of lambda in ridge regression and what happens if we choose it incorrectly? Just give me a minute. How do we decide the optimal value of lambda in ridge regression and what happens if we choose it incorrectly? This is your question. Okay. Just a second. How do we decide? Now you try to see here in case of your ridge regression. Am I sharing my screen? Yeah, I'm sharing my screen. Oh, good. So in case of your ridge regression, in case of your ridge regression, regularization parameter would be your lambda. Okay. It will control the trade-off between the empirical risk of minimization and the coefficient shrinkage. Okay. That particularly will be beta hat, that is minimum argument of y minus x beta, okay, plus lambda beta and square of all those two variables. So lambda is the bias variance optimization problem. Okay, so how you will decide that particular ridge regression lambda? Okay, first thing is either you can go for k-fold cross validation. Okay, that is in itself a challenge for you me to explain, or you can use it with scikit-learn or MATLAB R gamut, or you can use your generalized cross validation means K, or you can use Bayesian interpretation, or if lambda is chosen is incorrect. Okay, if lambda is too small or approximately equal to 0, your beta will be having higher variance, overfitting, invisibility. If it is too large, the coefficient will shrink almost to zero, it would be having high bias, underfitting, or loss of signal. Okay. Geometric interpretation is that it should be less than equal to t. Okay. So bias variance behavior is like this. As lambda increases, bias increases, variance decreases, trending error increases, results in a U-shaped curve. And optimal lambda will be based upon minimum test mean square. This is the one line answer to your problem. Okay. That is based on minimum test MSC, optimal value of lambda in regression, and what will happen if it is chosen incorrectly. I will try to explain. Okay, if it is, if you are choosing it too small, okay, it will have higher variance, overfitting, poor test performance. If it is too large, you will still be having high bias, underfitting, loss of signal of latent predictions. And how to choose it optimally? By going for minimum test mean square error. Okay. This is the answer to your question. If it still is not clear, then feel free to ask. Yeah. If two models have similar R square values but different MSE values, which one should we trust more and why? Yeah. This is a very in general question. Okay. If two models are having same R square values but different MSE values, which one should we trust more and why? You are having same R square values. It would be next to impossible that it would be similar to three decimal places. Okay. It's still, I am considering your case. That model 1 is having R square 0.961. Model 2 is also having 0.961 R square. Okay. Different MSE values means, let us suppose MSE 1 for the model, for model 1, the MSE is suppose 2.549, and for model 2, MSE is 9.763. So definitely you have to choose or you have to trust the model 1 because it is having minimum MSE value. Okay. Minimum MSE means over the entire range of Y predicted, it is having minimum error across the entire spread of Y. Okay. So that is your answer, that you have to always go for minimum mean square error. Okay. Now you try to change this particular question. Two models are there which are having different R square as well as same MSC is coming. Okay. Then in this particular hypothetical case, you will go for the model which is having higher R square, higher R square value and minimum MSC value. That you always have to choose. Okay. That will give you uh, most accurate results for entire domain range of x and y's. Okay, this you can practically demonstrate also. Fit n number of models. There is a particular library named as PyCal. Fit all the machine learning models. Okay, starting from linear regression to multiple linear regression to Gaussian progression regression. Fill Try to fit all the x and y variables values. Now, when it comes to choosing a model, you always go for the model which is having highest R square along with minimum mean square error, RMSC, root mean square error, or MSC. As well as we go for testing MAP also sometimes. Any more doubts? Anyone having any more doubts? Feel free to ask. The rest you can kindly leave. Yes, do join the session next week, same time, same link. Okay. And thank you all for joining the session. Yeah, if ridge regression reduces overfitting by shrinking coefficients, why can't we always use ridge instead of linear regression? No, it depends on the variability of data. Ridge regression not always reduces the overfitting by shrinking the coefficients. This you must have seen in one, two, three, four cases. Okay, but not always it will try to shrink the coefficients. You have to go for plotting the confusion matrix. Then only you will be able to tell that which parameter is influential, what is the influence of that particular parameter on the machine learning model or on the ridge regression model. Then only you will be in the position to say that what exactly has to be done. Okay. So not always it is that particular case that ridge regression will always reduce your overfitting, it will shrink the coefficients. Okay, linear regression. Why we are just progressing from linear regression? That question always comes in my mind also. When I generally see that random forest model or Gaussian progression regression model or all the advanced machine learning models or regression models, they are giving me good results. Why I am going with starting with linear regression model. Why? Because it particularly gives me the idea that which particular independent variable has the most influence on the dependent variable and which is not having any influence on my model, on my dependent variable. Okay. That particular idea, first of all, I have to get, and that is only possible in linear regression by plotting the linear regression. Afterwards, I am using ridge regression to shrink the coefficients or to reduce the overfitting, okay, and remove any underfitting if it is there to refine my results. But that the general idea I am always getting with my linear regression model only, okay. And not always you would be able to reduce the fitting, reduce the overfitting and get that much accuracy which is desired for the particular applications. Okay. So that is why it is best practice first to apply the plain linear regression, then go for advanced, then go for refining the results using ridge regression to reduce overfitting or remove any standard error variation. Okay, that also you can. That is the thing. Instead of simple train test split, why you would use for cross validation? It will give a more reliable estimate of the model performance. Yes. Definitely. Why is it giving me? Because try to understand simple train test split you are doing it means you are not accommodating the variability inside your train test data sets which you have created separately. Okay. You are not creating that particular variability in your train test split. Okay. That is why you are your model is not reliable in case the values come from outside the training, testing, and validation data sets. But if you are using any type of cross validation, k-fold cross validation, or n-fold cross validation, or simple bagging technique, then you are incorporating your variability in your data set, training data set as well as test data set. It will in general produce a more reliable model because the same variability which was there in the entire data set that you have tried to accommodate in your training data set, testing data set, and validation data set. Because you are creating simple batches of the data set and you are taking one sample, two sample, three sample as training, testing, validation. Then your the entire process is repeated. But if you are going for simple train test split, then randomly you are splitting the data sets into 70, 20, and 10. It will not accommodate the variability into your data sets into your training data set, testing data set, and validation data set. That is why your model will perform poorly when it goes into real field testing or performance evaluation on unseen data. That is the thing. Okay. But if you are going for cross validation, you will obviously produce more reliable model. That is right. In your high dimensional data, when the number of features approaches the number of observations, how does linear regression behave? And why does regularization in those particular cases become essential? See, in case of a high dimensional data, what is first of all high dimensional data, which is having more number of dependent variables. Okay. Number of features approaches the number of observations. Number of features approaches the number of observations. Yes, it can be there. Linear regression in that particular case will behave, how it will behave. See, it can behave very good, it can behave very bad, it can produce very high R square, very low MSE, it can produce very low R square, very low, very high MSE. Depends on the nature of the data. What is the correlation? What is the dependence of dependent variable and independent variable? That you have to tell me. Then I will be able to tell you that what how exactly the linear regression or any regression model will behave. Okay. And why regularization is becoming variable? Because the number of features is increasing. As number of features is increasing, we have to always look for interdependency between the features. Okay. That is why regularization, the role of regularization comes into play. Okay. See here, I already told you that expected value of the error should be equal to zero, means the errors or the dependent variables, they shouldn't have any dependence on each other. Okay, if they are having any dependence, then we have to take it into the play. And for taking it into the play, we are going for regularization techniques. That is in short your answer. Okay. And why regularization becomes essential, that can be determined mathematically also. I can prove mathematically also, okay, but it will take another 1 or 1.5 hours to explain you that. But keep this in mind. Okay. Shortest and simplest explanation I have provided. Yes, thank you. Thank you so much for joining the session. Do join the session next week, same time, same link. Okay. Any more doubts are there, then I'll stay. The rest I'll also leave. You can kindly leave. Okay. Do join the session next week, same time, same link. Thank you all for joining the session. Okay. And I hope that I have given you mail ID also. If you are having still any doubts, feel free to ask. Okay, I'll reply as and when I will find time. When the number of features becomes comparable to or even greater than the number of observations, how does OLS behave? And why does regularization become necessary in high dimensional settings? Same answer. Number of features become comparable to or even greater than the number of observation. Any linear regression, OLS model, multiple linear regression model, it will trying to behave in an unexpected manner, or it will not be unexpected. What will happen? The dependence between the features, the features which you are taking independent, they will try to show some dependence. So in that particular case, what will happen? The behavioral pattern which you want to track, it would be same only. Your R square and your MSC, they will not be in a range acceptable. That will be the case. Okay. So OLS, even linear regression, they will behave similarly. Why? Because these are the models which will try to accommodate. Okay. They learn from the Y and X values and even with the error. Okay. So that is the thing. So it will behave exactly same only. Okay. Regularization will always be necessary in case of your high dimensional settings, because you want to determine what exactly is the correlation of the dependent and independent variables, which are the variables uh, uh, which are highly affecting the performance of the dependent variable. Rest all the parameters you will try to minimize. Okay. Rest all the parameters you will try to eliminate, or you will try to minimize their effect on the regression equations. Yeah. So same question you have repeated, not a problem. But if you want to ask the effect of high dimensional settings on any linear regression model, or even on the machine learning models, any of the machine learning models, GPR, MLR, random forest regression, that would be same only. Okay. Effect would be same. Why we are doing for regularization? Because we want to produce R square and MSC in the range which is acceptable to us. That is the thing. Okay. R square should be maximum, MSC should be minimum. That is our criteria. Okay. That we are trying to fulfill. Why do sometimes standardize features before applying ridge regression, but not necessarily for basic linear regression? See, See, you can do regularization. There is nothing. Okay. Sometimes you are trying to say, why do we sometimes standardize? We always have to standardize the pieces. Okay. It is not the case that sometimes you will adopt different procedure for ridge regression, different procedure for linear regression. That I don't know where you have seen code the exact reference, then I will be in a position to comment. Okay. But the standard procedure says that you have to always go for standard variation. It will improve your results. Whether it is your linear regression or ridge regression, OLS regression, any MLR, GPR, anything. Okay. So sometimes case you have seen, according to me, it shouldn't be there. Okay. Because the standard procedure which is there, we have to always go by the book, which says go for standardization, go for correlation, go for correlation matrix plot. Okay. See which are the variables which are affecting the dependent parameter most. And then you try to formulate the regression equation. Thank you, sir, for clearing all my doubts. You can explain concept very clearly and make them very clear. Thank you so much, Devasti. I am here to clarify all your doubts only. Okay. So, meanwhile, if you are having any doubts, I have also given my mail ID. Feel free to contact me, but do clarify before the examination all your doubts. Okay. And I am also obliged to you that you find my explanations correct and it's simple to understand. Okay. Okay, hence I'll end the session for you all guys. Thank you all for joining the session. Do join the session next week, same time, same link. Thank you. Okay, I'm ending the session for you all. Thank you once again.